Welcome to the next video of me refamiliarizing myself with Maxwell's equations. This is going to be the last video. It's going to be brief. I'll explain at the end why. Uh, so we're looking at the last one, the integral form of Ampere-Maxwell law. Excuse me. So the original Ampere's law was only this part here. And Maxwell added this part, right? So in the book, A Student's Guide to Maxwell's Equations by Daniel Flesch, which is where all this comes from, he gives this nice little explanation here, and it's way better than I could do. So let's just use what he's got. Okay, so he's saying the inner product of the magnetic field with the segment of this path C. So this is a closed integral along a path is equal to this constant times the enclosed the current, but also you can get a contribution from the field if the current is varying. So the current is a function of time. You can get this contribution to this dot product also, right? So that's what all this means. This is just Gauss's law. We did this the very first equation, the very first video that we did. So there's a lot going on here. We're just going to look at one little piece of it. Okay, in back in video number 5, we used an underived equation, which was the field is equal to these constant times the current over the radius times this unit vector of phi hat. And I hated it that we used this and he didn't explain where it came from. Well, this is where it came from. So we're going to do that. Okay, here's the problem. A long straight wire of radius R0 carries a steady current I uniformly distributed throughout its cross-sectional area. Find the magnitude of the magnetic field as a function of R, where R is the distance from the center of the wire for both R greater than R0 and R less than R0. We're just going to do this first part because the rest of it's kind of boring. Okay, so here's a nice drawing that he provided, right? So R0 is the radius. This is a blow up of a cross section of a piece of wire. R0 is the radius of this. So he's saying R greater than R0 is this imaginary loop going around this wire, which he calls Amperian loop number 1. So like something from Star Trek. All right, so since the current is a constant now, and he gave that in the problem, a steady current means it's a constant, right? We only need the first part of the equation. We don't need the time varying part of the law. We only need this part. Remember? So here's the whole equation. And since the current is a constant, it's not varying with time. So this part goes to 0. So we only need this part. All right. So what are we going to do here? Remember back, we had this drawing already. So this is cylindrical, the coordinates. And you can see that the part of this that we're interested in is this part here, phi hat, which is that parameter which swings around the z-axis, right? Which swings around the z-axis. So you can see that this is a cylinder, right? So the phi hat unit vector is tangent to this all the way around. Everywhere it goes around is tangent to that. So that's the only part of the vector we're interested in. So we can say that the magnetic field and this incremental line element, they're both in the phi hat direction and they're parallel to each other. So the dot product becomes just the magnitude of B times the magnitude of this DL times the cosine of the angle between them. Well, the angle is 0, so cosine of 0 is 1. So we just get this. So that greatly simplifies it for us. So we write it like this. Now, so we have the magnitude of both. This becomes a constant. And what's the DL? Well, it's just a circle. It's just this thing going around, right? It's just 2 pi r. So there's no need to integrate because it's right there. So we get this equation and we want to then solve for b. And since we needed in a vector, the format, we just said it was going only in the phi hat direction. So we make it a vector equation. So this is where that came from, Ampere's law. And we used that already in one of our problem, the solving, and it bugged me where this came from. Okay, so the reason I started this series anyway is because I bought this book, Geometric Algebra for Electrical Engineers, Multi-Vector Electromagnetism, because I'm interested in geometric algebra. I don't know why. I just find it fascinating. And this jumps straight into Maxwell's equations, boom, right in your face. And I just didn't remember them. I mean, it's just been too long since I studied them in school, never used them again the rest of my life. So I don't remember them. So that's why I bought another book, which is this book, A Student's Guide to Maxwell's Equations by Daniel Flesch. And just like I was so happy with his vector and tensor book, I'm very happy with this book. I'm telling you, this guy, he's good. If you have had general physics, so you did some E&M in general physics, and then you've had some introduction to the vector, the calculus, this is a great book. You will learn how to use these equations from this book. I highly recommend them. So anyway, I'm no expert at this point. I don't want to be. I just needed to get my feet wet with Maxwell's equations so I can study this book on geometric algebra. So that's it, and I thank you for watching.